Hey guys, welcome to the last official lesson on organic chemistry. Today we're going to be looking at radical reactions. Here's a little bit of a joke, similar to what Lee might do. All right, so today we're going to describe the steps of a radical reaction, and then we're going to find out how we can use those steps, or at least we're going to use one or two of those reactions to help us with our synthesis. Okay. And I have a molecule of the day today. I haven't had one in a while because we've been doing reactions for a while, but this is a really interesting one. It's called resveratrol, which is the antioxidant molecule found in grapes, and oftentimes the excuse that alcoholics give to drink wine. And what this molecule does is considered to be an antioxidant. And as you guys know from like maybe pop culture, is that antioxidants are like anti-cancer or cancer-fighting molecules. And there is like a little bit of truth to it, not entirely. Like it's not as like a miraculous as you might think, but there's still some truth to it. So let's talk about what that is. UV light from the sun or from any kind of UV source is high energy, and so therefore it's dangerous. But why is it dangerous? And the reason for that is because it can create radicals in our cells, and radicals are essentially atoms that have only one electron. So we talked about like carbon having a positive charge. We talked about carbon having a negative charge, right? And so when you have a negative charge, in fact, that negative charge is represented by a lone pair, an actual two electrons. And so a radical is actually, when it's not a lone pair, it's a lone electron on its own. So this is a radical. All right, and this radical, excuse me, this radical This radical is quite reactive. In fact, very reactive. And it reacts with even in the most inert molecules. And so having this in your cell could be quite dangerous. Specifically, why it could be dangerous is that it could cause mutations in your DNA. So it reacts with the double helix and can cause it to have mutations. And then when you do DNA synthesis and you replicate the DNA just before mitosis, you will replicate it with some mutations, and therefore you're propagating an error in the genetic message to the daughter cells. Then, of course, that error gets transcribed and translated into a protein, and then it might do something that it's not supposed to do. And those are usually the kinds of things that lead to cancer. Now, why is resveratrol a anti-cancer agent, or why are antioxidants anti-cancer causing agents? Well, the reason for that is because they have a very highly conjugated aromatic system. So here you can see you have two benzene rings separated by conjugated alkene here. And so what's great about that is that it's called an electron sink. And when there's a huge amount of aromaticity, adding a few electrons in there doesn't destabilize the molecule all that much. So if a radical is going to choose to do damage to something, it's going to choose to do damage to something called an an electron sink, because that's where that's where the electrons are going to have an affinity to go to begin with. So what ends up happening is that the radicals get trapped in this sink, kind of like a faucet, like a kitchen sink in that kind of sense, where the electron could be localized in any one of these carbons along the molecule that are conjugated with a double bond. And through resonance, you're playing that game of hot potato, where the radical is passed along each carbon. And so when it does that, the damage is being done to this molecule, and this molecule you just kind of like pee it out, and so it goes away. The molecule that it normally attacks when this is not in this place, or when antioxidants are not in the cell, are your DNA molecules, which are electron sinks on their own. So they have aromatic rings that kind of look like this. They have aromatic rings that kind of look like this. These are called pyrimidines. And yeah, and these are electron sinks because as you can tell, they're conjugated and aromatic, and so therefore the radical will get stuck in there and cause damage. So this is kind of like a decoy, I guess, if you will. However, the half-life of this in your cells is very low. So you got to be drinking like 24/7 for you to actually have like a tangible benefit from quote unquote drinking wine and fighting cancer. You'll have serious other issues like liver failure and you'll die sooner from that, but at least there won't be cancer. All right, so steps in a radical reaction. Now, this is like the part that's going to be required for you in terms of mechanism. And so what you need to know in a radical reaction is that there is three steps: initiation, propagation, and termination. And one thing you'll notice here, which is different from what we've been doing before, is that before, when we drew an arrow, we drew it with two sides to the arrow, whereas over here, we draw it with only one, okay? So when you draw an arrow that has two sides to it, it means you're moving two electrons. Two electrons. And when you move it with only a one-sided arrow, that means you're moving only one electron. Okay? So over here, what you have is this bond, this chlorine bond, that's made up of two electrons, and this bond is going to separate, and electrons are going to go their separate ways. So that's why a bond breaks, and then one electron goes to the left, and one electron goes to the right, and what you end up with is two chlorine radicals. All right? This is the initiation step, because you went from having no radicals to having two radicals. Okay? So that's the initiation. All right, in the propagation step, whatever you have before the arrow, you're going to have after the arrow. So here you have one radical, right? One radical. And after the arrow, you also have one radical. And you can have one radical and one radical. And these could actually propagate because it's propagation. These can actually propagate over multiple reactions before it actually terminates. So the propagation step can be quite complex. In this case, what's happening is that Cl is forming a covalent bond with H to form HCl, and therefore H has to get one of these arrows, get one of these radicals in order to make the bond with chlorine. So in fact, what you would do is you would draw it like this. Oh, not a two-sided arrow, but a one-sided arrow. You would draw it like this. And then this part of it is going to go to the carbon. And so now you can see that the radical is on carbon and hydrochloric acid has been produced. Then this could happen again, and you can have two radicals coming together to form another bond. So now I have chloromethane, and then I've reproduced my chlorine radical. Okay, so these can continue to go on. And this is not a specific reaction here that I'm showing you. It's a very generic one. You don't need to know this one. What you need to know from this slide is how to draw the arrows. What I want you to notice in this propagation step is that I had one radical before the arrow, one radical, arrow, and then I look at my products, one radical. Over here I had one radical, whoopsie. Over here I had one radical, and over here I have one radical. And then finally, in the last steps of when this reaction is finally going to be finished, is when two radicals come together, right, and form a bond, right? So here I had two radicals. So this is the opposite of a initiation. And you had no radicals. Two radicals, no radicals. Again, these are examples. I'm not showing you a specific reaction. Two radicals, no radicals. And those are, in general, the broad strokes of what a radical reaction looks like mechanistically. Okay. And now there are two reactions that you guys need to know for this course. Well, I guess I should mention the stability of this. So similar to carbocations, it's the tertiary that are more stable than the secondary, that are more stable than the primary, that are more stable than the methyl radical. Okay. And what's important here is that there is no possibility of hydride or methanide shift. No possibility of hydride and methanide shift. But resonance stabilization is possible. Okay, so knowing that, we can take a look at a couple reactions and see what's going on. The first one is one that you've learned already, and there's a mistake here in this slide. That's not Br2, it's HBr. And this was in your alkenes reaction, all right? And so the mechanism, we can go over it now because we didn't look at the mechanism before when we did alkenes. But essentially what this did was it was an anti-Markovnikov reaction to add a bromine group to the alkene. So the first step is that UV light will damage this peroxide. So the peroxide I'm going to use is just hydrogen peroxide. And so UV light damages this, and you produce the radical. Okay? And what you get is 2 times OH. 2 times OH with a radical, though. Not OH minus, but OH radical. All right? And then what you produce with this OH radical, so I'm going to take this OH radical, and I have HBr, is I'm going to produce a bond with the hydrogen, and the bromine is going to have to take one of the radicals. So what I produce here now is H2O plus Br radical. Okay. By the way, if we're using our terminology, this is the initiation, and this is a propagation step. All right, so now we're going to actually have to react it with the alkene, and this is the tricky part because you have to remember that a radical is more stable on a tertiary, more substituted carbon. So if you're looking for stability on a more substituted carbon, then you need to know where the double bond is going to expand. Okay. So the first thing that's going to happen is you have this, and you have your Br radical. So this double bond is going to break and form a bond with the bromine on the least substituted. And the reason why it's on the least substituted is because that means that this carbon is going to be the one that's left over with the lone pair, with the lone radical. Okay. So far, so good. And then the last step, what's going to happen is you're going to take water, and it's going to pair up with one of the hydrogens in the water, and then you're going to regenerate that OH radical. Okay. So the OH radical was never used, all right? It was remade at the beginning. And so it's more kind of a catalyst than it is a actual reagent. But it is necessary for the reaction. Okay. And so there it is. There's the anti-Markovnikov bromination. Bromination of an alkene. Okay. The next reaction is also very interesting. Is this, and this reaction is quite interesting because you're starting off with an alkane, which is basically inert, but if you put it in the presence of strong UV light and chlorine, you'll actually chlorinate the alkane, right? So you're adding a leaving group to something that didn't have a double bond or anything like that. That's very interesting because it's a great way for us to use that in synthesis. Now, how do we get something to have a leaving group on it? And so there is a process for this, which involves with this whole radical reaction thing. And I won't show you the mechanism because it's a little bit complicated, but suffice it to say, it still has an initiation, propagation, and termination step. And what's important to remember is that here you're going to get a more substituted chlorine or halide, alkyl halide. And here you have a primary alkyl halide. And this is going to be the major product, okay? So this produces an alkyl halide on the more substituted carbon of the molecule, okay? And as we know, the tertiary is even more substituted. So if I had something that was tertiary, then they would prefer to go there, okay? And then finally, you have that same reaction, but instead of chlorine, you can do it in bromine. And again, you can have the minor product, which is this. But this is still the major product. And that's super useful for synthesis. And the reason for that, as I told you before, is so that we've introduced a leaving group to a molecule that's relatively inert, and then we can do a whole bunch of fun stuff with it with regards to SN1, SN2, E1, E2, alkene reactions, alkyne reactions, and so on. So this is a really great tool for synthesis. And that's pretty much it for radical reactions that you guys need to know. That's it for now. Take care.